This presentation reviews ordinary regression. This brief presentation was organized by Dr. Alemi. We begin our discussion of regression with clarifying its purpose. Regression is a general method that relates an outcome variable y to one or more independent variable x1 through xn using an equation. Equations are important. They precisely show how variables affect each other. They are the language of science and allow scientists to express their theories. Regression is a procedure for fitting data to an equation. The analyst specifies the equation, and the software fits the data to the equation by estimating the parameters of the equation from the data. These equation parameters are also referred to as regression coefficients. We use the terms coefficient and parameter interchangeably to break the monotony of a commonly repeated word. Regression can be used to predict future stock market values from their current and historical values. Regression can be used to assess the impact of health promotion and components of media campaign or recruitment of a new patients. It can be used to predict likelihood of a sale or market penetration given the characteristics of the population in the zip code area. Regression can be used to predict likelihood of project success from its characteristics. Regression can be used to assess financial risk from historical patterns. It can be used to assess the likelihood of bad debt from patients' characteristics. It can be used to check for fraud by comparing amount charged to amount expected based on patient or provider characteristics. Regression can be used to assess the effectiveness of medical interventions. It can be used to identify the relevant components of care that lead to cost overruns. Regression can be used to summarize the impact of different surgeons on overall cost of bundled care. It can be used to identify relevant risk factors that increase patient risk of illness, patient's risk of compliance with treatment, or likelihood of adverse outcomes. Regression is a versatile tool and is widely used in many different situations. In multiple regression, we have one dependent variable and many independent variables. The dependent variable y is described as a function of multiple independent variables. Here, the dependent variable y, for example, cost, is shown as a function of two independent variables x1 and x2, for example, age and gender. There could be also many more independent variables besides the two we have shown here. The equation starts with a constant b index 0. This is the intercept of the line when all independent variables are 0. The main effect of x1 and x2 are captured by parameters b1 and b2. The effect of interaction between the two variables x1 and x2 is captured by the parameter b3. The interaction term x1 times x2 is the product of the two variables. The interaction of two binary variables is present when both variables are present. If one is missing, it takes the value of 0. Then the interaction term is 0 too. In regression, the equation of a straight line is used often. Regression parameters for a straight line equation are the intercept and the slope, same terms as what was used to describe a linear equation. The coefficient beta 0 is the intercept. The parameter beta 1 is the estimated slope. We use the hat on top of y to indicate that it represents an estimated variable calculated from independent variables. It's not the observed value of the outcome, but an estimate from the formula. We also show the slope and intercept using Greek lettering to emphasize that these are estimated from the sample data. To accurately estimate the intercept and slope parameters, regression calculates a residual. Residual is the difference between estimated and observed dependent variable. Regression minimizes the sum of squared residuals. For a straight line, the intercept beta 0 and the slope beta 1 parameters are estimated to minimize the difference between observed y value and predicted values. In this table, we have used the regression equation to predict a value for y. The residual is the difference between the observed and predicted values. The square of residual is given at the column to the right. The sum of these squared residuals tells us how well we have fitted the equation to our data. In this figure, we show the linear relationship between y and x. The predicted values lie on the line. The differences between the observed and predicted values are shown as a dashed line. At x equals 1, there is no difference. At x equals 4, there is a small negative difference. The largest difference is at x equals 3. The positive differences are at x2 and x equals 5. Each one of these differences is considered as a residual. Regression is fitted to the data so that the sum of the squared residual is the smallest possible number. The line in this figure has the sum of squared residuals of 4.8. Different lines are fitted until a line is found with the smallest sum of squared residual. Different lines will have different sum of squared residuals. The objective of regression analysis is to choose regression parameters so that the line has the minimum sum of squared residuals. The 5 lines on the left show the sum of squared residuals associated with lines that have different intercepts but same slope. The ones with the lowest sum is the solid blue line, and this is in fact the regression line. The same for the right-hand side. In the right-hand side, 5 lines are shown with different slopes. Each line has a different sum of square residuals. Again, the line with the lowest sum is the regression line. Again, the solid blue line is the line with the best fitted slope. You may reasonably ask why the squared residuals should be minimized. This is a heuristic, and there is no mathematical reason for it, except that such a sum allows one to easily calculate the parameters of regression. By easy to calculate, we mean that it is not necessary to repeatedly try different lines and see which one has the minimum sum of squared regression residuals. A formula for estimating the parameter that would produce the minimum sum of squared residuals calculation has been worked out. No need for minimization. The formula guarantees that the estimated parameters would produce the minimum sum of squared residuals. Regression has two sets of variables, dependent and independent variables. In this section, we discuss how to prepare these variables for analysis. In an ordinary regression, independent variables can be binary, categorical, continuous, or interaction variables. In ordinary or standard regression, the dependent variable is a continuous variable. Ordinary regression estimates the mean of the dependent variable as a function of independent variable. Binary or dummy variables are assigned two values, 0 or 1. They are used often to indicate the occurrence of an event, such as the occurrence of an intervention or adverse event. Categorical variables have multiple discrete levels. These categorical variables must be turned into binary variables before conducting the regression. For each category, a new binary variable is created. One of these binary variables is dropped as the combined absence of all the other variables implies the drop variable. The drop category will act as a reference point for the comparisons of all other categories. For example, consider patient's race. It has multiple categories including white, black, Asian, and other. Each category can be turned into a new binary variable. Thus, we can have binary variable called white. Its value will be 1 if the patient is white and 0 otherwise. Another binary variable called black will be 1 if the patient is black and 0 otherwise. Still another variable called Asian will be 1 if the patient is Asian or 0 otherwise. Finally, the variable other race will be 1 if the patient is none of the listed races and 0 otherwise. The single categorical variable called race was broken into the following 4 binary variables assuming values of 1 and 0. Then, instead of regressing cost on race, one has to regress the dependent variable on several binary independent variables, each standing for one type of race. Since 3 out of the 4 binary variables indicate all possible patient races, then one of the binary variables is left out. The category left out is referred to as reference value. Suppose we select white as the reference value. This is the situation where all the other 3 indicators are 0. The regressing on black, Asian, and other categories is sufficient to estimate the impact of race. The intercept B0 in this equation estimates the impact of white race. The slope for other race parameters indicate the impact of black, Asian, or other race categories. Continuous or interval variable can enter regression as they are without transformation. Interaction variables are the product of 2 or more variables. In multiple regression, the main effect refers to the impact of the variable by itself, and the interaction effect refers to the impact of a combined set of variables. Interaction between 2 or more variables is modeled by the product of the variables. For example, consider 2 binary variables where when the variable is present, it is coded as 1 and 0 otherwise. The product of 2 binary variables is another binary variable which is 1 when both variables are present and 0 otherwise. With 2 binary variables, 4 situations are possible, and the only time the product is 1 is when both variables are present. If one variable is binary and another continuous, the product of the variable would be 0 when the binary variable or the continuous variable is 0 and otherwise same as the continuous variable. If both variables are continuous, then the product of both variables will be continuous and a larger number than the sum of the 2 variables. Including interaction terms in regression expands our ability to model events. Once the data has been prepared, the next step is to run a regression. You can do a regression using Excel. To use Excel to do regression, you must first add in the analysis toolpack. This is done by 1. Clicking on Excel logo, 2. Clicking on add-ons from the vertical menu list, 3. Selecting Manage Add-ons, and then 4. Clicking on the Go. Once the menu for add-in comes in, then select both the analysis toolpacks. The first 6 steps had to do with adding in the toolpack. Regression is one of the options in the analysis toolpack. The regression menu requires the specification of input variables. The dependent or Y range must be specified. The dependent variable must be numerical with no missing value or text. A common error in Excel is that one of the values in the dependent variable is entered as text, making it impossible to run the regression. The range for the independent variables should also be specified. This range must be as long as the dependent variable. Up to a maximum of 250 variables can be included in this range. If the first row contains name of the variable, check the box next to labels. If there are no intercepts allowed in the regression equation, a rare situation, check the box constant is 0. The output options must be specified and make sure that you do not designate the output to be the same place where you kept the data, as it will wipe out the data. Options on residual plots can also be specified. The normal probability plot tests the assumption of normal distribution of variables. You can do a regression using free software online called R. R is an open source free software which can be installed from this link. Before reading data into R, we need to check that we have set our working directory properly. In R, this can be achieved by using the getwd open parenthesis close parenthesis command. It provides what is working directory for R. In my computer, it resulted into the result shown. What this means is that R is currently set up to look for files in the users/hap directory on my machine. Let us assume that our data is stored in the user/hap/documents directory, and so to change the R working directory, we need to use the setwd open parenthesis close parenthesis command. The easiest way to read data into R is to use comma-separated variable CSV files. Our data file is titled mfhcleaned-up.csv, and to read this into R, we need to use the read.csv command. What we have done here is to tell R to read the data into an object called mfh in our R workspace. We can check the type of the object mfh through using the class open parenthesis close parenthesis function. Now we know that we have set up a data frame. A data frame has all the data needed for the analysis in a matrix format with headings and related information. We are now set to proceed with the analysis. Our code requires us to call a function called lm open parenthesis close parenthesis. The column listed before the tilde is the response or dependent variable, and the column listed after it are the independent variables. The first set of output is the distribution of residuals shown in terms of 5 points: minimum, first quartile, median, third quartile, and the maximum. One expects to see a normal distribution which is symmetric around the median. The coefficients list the intercept and age parameters. The probability that the t-statistics calculated from the observed coefficient is different from 0 is also provided. There are three components to the regression output. The first has to do with coefficients of the regression equation. The second output has to do with goodness of fit. The last set of output are a series of plots and statistics that can be used to test regression assumptions. Regression output provides the coefficients for the equation we have specified and their statistical significance. If there are no interaction among the independent variables, the slope parameter estimates the per unit change in the dependent variable as a function of 1 unit of increase in independent variable. The slope is the ratio of the rise in y to run in the x variable. A note of warning is necessary about the effects of interactions or interpretation of regression parameters. Interaction terms change the interpretation of the regression parameters. When interaction terms are present, the regression coefficients no longer indicate the rise in outcome for the run in the variable. In fact, the notion of a run in a variable is no longer clear. Everything we mentioned about interpretation of the coefficient as slope of the line is not valid if interaction terms are present. In a way, our effort to explain regression in ways that could help create intuitions about it has put us in a pickle. Our explanations do not work when interaction terms are present. So what's the meaning of regression coefficients when interaction terms are present? There is no simple answer to this question. The coefficients are the parameters of the equation, and they may not have a meaning other than being a number in the best fitted equation. Regression output also provides the probability of observing the estimated coefficient. If this probability is small, say smaller than 5%, then there is a statistically significant relationship between the dependent and independent variables. The regression parameters are estimated from a sample of data. If multiple samples are taken from the same population, the estimates for the parameters will be different for each sample, even though all the samples are taken from the same population. This sampling variability gives rise to a standard error associated with each regression. The common way to address the uncertainty with estimates is to develop 95% confidence intervals and p-values. The 95% confidence interval for the intercept or for the independent variables are calculated from the standard error of the estimates. Regression coefficients and their associated standard error can be used to test hypotheses. The null hypothesis states that the real population coefficient beta 1 is equal to 0, whereas the alternative hypothesis would be that this coefficient is not 0. For the coefficient assuming null hypothesis to be true, then the standardized t-statistics can be calculated from the standard error of the estimate. The t-statistic calculates the number of standard errors the estimated coefficient is away from 0. Testing hypotheses using regression coefficients may lead to findings that are different from direct test of hypotheses covered in typical statistical classes. The coefficients of regression equation are affected by other variables in the equation. When certain variables are present, a hypothesis may be rejected, but when these variables are absent, and the same hypothesis may be accepted. In short, regression provides a context-specific test of hypotheses. Regression output also provides goodness of fit statistics. These statistics report how well the data fit the regression equation. The R squared is used to measure the goodness of fit between the equation and the data. It reports the strength of association between the outcome variable denoted by Y and the independent variables. The value of R squared can be anywhere from 0 to 1, where 0 highlights no association at all and 1 represents the strongest possible association. An R squared of 1 indicates that the independent variables perfectly predict the dependent variable. Since this only occurs when the prediction task is oversimplified or overspecified or tautological, one never sees an R squared of 1. The statistics R square estimates the percentage of variability in the outcome variable explained by independent variables. The total sum of square is a measure of the variability of observations around the mean of the observations. The unexplained sum of square is the sum of the square of the residuals, where residuals are the difference between observed outcome and predicted outcomes. The difference between the total sum of squares and sum of squared of residuals is the explained sum of squares. The coefficient of determination is calculated as the ratio of explained to total sum of squares. One particular problem with R squared is that it increases whenever a new variable is included in the model. In other words, one expects the fit to the data to become increasingly accurate as the number of variables increases. The adjusted R squared corrects the R squared value by the degrees of freedom available. Thus, it allows one to examine if the addition of a new variable increases the adjusted value and thus makes real improvement. Keep in mind that the statistics R squared is sensitive to the size of the data. As the size of the data increases, there is more variability in the data, and a small percentage of variability could be explained by a fixed set of variables. Thus, for very large data, for example, millions of patients, 100 independent variables may explain 25% of the total variability. Despite the low number, this may be a reasonable model. For a small data, for example, 2,000 cases, 100 variables may explain 80% of variability. An R squared of 25% may be low in a small but reasonable in a massive database. In small data, there are less variability to explain to begin with. In developing regression model, it's important to keep in mind the two competing considerations. The first is that one wants a model that accounts for most of the variation of the dependent variable. In other words, develop a model that maximizes the coefficient of determination, the explained proportion of variation in the dependent variable. A large portion of the variation in outcome can be explained by including more independent variables in the model. The second consideration is that regression models should be as parsimonious as possible. The simplest model that has the highest coefficient of determination should be chosen. This criterion is maximized by selecting a few independent variables as possible. The analyst must examine several models and choose the model that has best predictions with fewest independent variables. In hierarchical regression modeling, two regression is done. Variables known to have strong relationship with outcome are put in the first regression. The percent of variation in outcome explained by the regression is noted. Then an additional independent variable or a set of additional variables are added and a second regression is done. If the percent of variation in outcome explained by the second regression is significantly higher than the percent explained by the original regression, then the new variables are retained in the regression. Otherwise, the variables are discarded. The process is continued until all new independent variables are examined. In this approach, the analyst decides on the order with which various sets of variables are entered into the regression. When the order is decided by the software itself, using the variable with the highest percent of variation explained first, then adding additional variable, the process is called forward stepwise selection of variables. In a forward selection, once a variable is entered into the regression equation of the variable is not taken out if other variables undermine its influence on the outcome. When we start with all independent variables and progressively drop one variable that does not explain the variation in the outcome, then the process is called backward stepwise selection of independent variables. To avoid overfitting the data, where the noise in the data is modeled, it's important that the performance of various models, whether hierarchical, forward, or backward, should be checked in a new data set, a concept known as cross-validation. Collinearity refers to a strong correlation among some of the independent variables in a regression model. Collinearity affects the variance of regression coefficient. Therefore, in presence of collinearity, the regression coefficients change. A simple view of the relationship between two variables assumes that one variable affects another. In regression, this simple view is often wrong. The effect of two variables on each other could depend on yet a third variable inside the regression equation. For example, in predicting cost of care, the effect of aging on cost could depend on gender, a different variable in the equation. If two independent variables x1 and x2 are correlated, then the impact of each of the outcome on the outcome y depends on the other. Another way of saying this is that if the two variables have strong correlations, then one of these variables can change a significant relationship of the other variable with the outcome to an insignificant relationship. In short, the impact of variables depends on other variables that are also in the regression equation. In this sense, relationships found in regressions are context dependent. With one set of variables, the relationship may exist. With another, it may vanish. The existence of collinearity may be anticipated by calculating the correlation matrix, the correlation between any two pairs of independent variables. It is not always clear what to do with collinearity. One could drop one of the two correlated variables, but that may reduce predictive accuracy and may make models that are sensitive to missing values. One can continue with both variables in the model, assuming that the observed coefficients may be affected. To use ordinary regression, verify assumptions, transform data, then interpret the results.